Good evening, students. Today I will continue with the next part of the simple harmonic motion. So in the previous two videos I have completed what you mean by the simple harmonic motion, what is the characteristics and the equation of it. Okay. So today I will explain the simple harmonic motion in terms of circular motion concept. Okay, so uniform circular motion basically. So let us begin. Suppose a particle P is there which is moving with uniform speed along the circumference of this circle. So this is basically the center of the circle O, right? A particle P is here. Okay. So when the particle is at the P point, then the foot of the perpendicular drawn from the particle on the diameter A dashed. So this is the A dash diameter. I am drawing this perpendicular. Okay. And this is Pn. Okay. When the particle was at B position, suppose here, okay, the projection was at the point O, and when the particle moving along the circumference reaches to the position A, so in this direction the particle is moving. Okay, the projection moving along the diameter also reaches at A. When the particles moves along the circumference reaches at this B dashed point, the projection moving along the diameter reaches from A, from here to here, right? Again, the projection moves along the diameter from O to A dashed. Okay, so like this. Here is one projection, again this is rotating, here is the another projection, then coming to this, then coming to this, like this way the particle is rotating and spending or doing the projections along these diameters as well. Okay. Now, when the particles goes along the circumference from B dash to A dash, the projection moves along the diameter O to A dashed. And when the particles moves from A dash to B, the projection moves A dashed to O. Okay. Thus the projection N moves. So this is the projection. So this projection is moving like this. Okay. So the projection N moves in a straight line along to and fro about the point O. So let us understand this very clearly. Suppose the P is here. Again, when P comes at this point, so this projection comes here. Again, this P point comes here. So this projection, this Pn comes here. And when this P point comes here, so these projections again come here. So first this position, then this position. Now this P comes here. So again this projection, if it moves like this, so this P again comes to this way. First the projection is here, then comes to here, then again here and here. So this is nothing but one to and fro motion like this. Okay. So therefore, thus if a particle moving with uniform speed along the circumference of a circle, then the straight line motion of the projection of the particle on the diameter of the circle is called the simple harmonic motion. So this is the diameter and this is the projection, which is just doing nothing like this, which is nothing but like this. It is moving like this. Therefore, it is called the to and fro motion. Therefore, as the particle is moving on through in an uniform velocity through the circumference of a circle, we are saying that it is moving with the simple harmonic motion. And this circle is called the reference circle of the simple harmonic motion. This is the kinematical definition of the simple harmonic motion. Okay. Now, the motion of the projection of the particle on any other diameter of the circle of reference will also be the simple harmonic motion. Here I have considering this diameter. If I consider this diameter, then also the projection will be like the simple. If I consider this, all of these are nothing but the diameter of the circle. So therefore, all of these will show the simple harmonic motion. Therefore, a simple harmonic motion may be defined as the motion of the projection of a particle at any diameter of the circle of reference. So, SHM may be defined as circle of reference. Okay. So this is the kinematical definition of the simple harmonic motion. Hopefully it is clear to all. Now coming to the displacement equation of SHM. Suppose, let us draw the picture again. Okay. So, suppose the particle P starts from the point B and revolves through the angle of theta in radian. It is theta. Okay. In t seconds. Okay. So, if, okay. If initially the particle P is in this position, now if it starts to rotate with an angle theta in radian at time t, okay, so at time t, and let us consider that angular velocity is omega, okay. So therefore the omega, what will be the omega? Omega can be written as omega equal to theta by t, as omega is the angular displacement. Therefore, theta equals to omega t. So, this theta is nothing but my omega t. Okay. So, in t second, the projection of the particle P on the diameter A dashed is at n. Okay. Then, ON, suppose this is on, that is y. Okay. So, ON is the displacement of the projection in time t. So, therefore, in the triangle OPN, what we have said? We can say that y equal to ON. What is ON? Now, look, if it is theta, it is also theta. As NP is parallel to OB, this is the transversal. So, these two are the alternate angle, right? So, therefore, it is theta. So, and it is the perpendicular. So, ONP is nothing but the right angle triangle. Therefore, ON is the height OP is the hypotenuse and NP is the base. So, ON is the height. So, we can write it as OP sin theta. Okay. Now, what is this OP? OP is the radius of the circle. Let us consider is at A as A. So, it becomes A sin theta. Right. Now, what is theta? Theta is already we know that it is omega t. So, the equation becomes sin omega t. So, we can write y equals to A sin omega t, right? So, this is called the displacement equation of the simple harmonic motion. Okay. So, what will be the amplitude of the SHM? The maximum value of this sin omega t is 1, right? So, what will be the maximum displacement? Let me delete first, remove this part. So, now if I consider that our equation is y equal to A sin omega t, right? Now, omega t, sin omega t becomes, if sin omega t becomes 1, then what will be y? Y equal to A, right? So, if sin omega t 1, y becomes A, and this A is basically the maximum displacement, and it is defined as the maximum amplitude of the motion. Basically, it is equal to the radius of the reference circle. Okay. Now, what is periodic time? What is periodic time? The time taken by n to complete one oscillation is called the periodic time T. It is defined as T. Okay. So, the time during which n completes one oscillations. The particle P completes one round of the circle of the reference, that is, it revolves through an angle 2 pi radian. So, what I have said, if this is P at time T, it completes one revolution. How much angular displacement was occurring? That is nothing but 2 pi. So, this complete rotation, that is 2 pi. Therefore, we can write that T equals to 2 pi by omega. So, this is the periodic time of n. Now, what is frequency? We all know the relation between frequency and time period, that is this. So, therefore, n, that is frequency, will be omega by 2 pi. Okay. Hopefully, this part is clear to all. Now, one new definition, that is phase. What do you mean by phase? Now, when a particle oscillates, its position and direction of motion vary with time. The phase of a vibrating particle at any instant express the position and direction of motion of the particle at that instant. So, what is phase? Phase is nothing but the position and direction of a particle at any instant, at that instant. So, the phase is expressed either in terms of angle theta or in terms of periodic time, that is T. Okay. For example, if I consider the previous picture, that is this one, if I consider this, so this is A, this is A dashed, this is B dashed, and this is B basically. Okay. This is O. So when P reaches at the point A, one second, sorry. So from this point, when P reaches at the point A, then what is happening basically? So what will be the phase? That will be pi by 2. Why pi by 2? Look, this is the first quadrant. This is the first quadrant. Total is 2 pi. So this is just pi by 2, right? So for the total rotation, T is required, as this is the 4 in terms of radian, that is pi by 2. If in terms of T I want to calculate the phase, so as it covers 1/4 of this circle, so the time period will be T by 4. Sorry, not the time period, that phase will be T by 4. If at any instant two oscillating particles are passing simultaneously through their equilibrium position in the same direction, then at that instant they are in the same phase. So at any instant, if two oscillating particles, suppose this is P and suppose this is P0, okay. So suppose this is omega t and this is in general phi, and this is considering as alpha, okay. So let me draw this solid line. Okay, so at any instant, if two particles are passing simultaneously, here P and P0, these two particles are passing simultaneously through their equilibrium positions in the same direction. Both of them are going in this direction, okay. Then at that instant, I will say that these two are in same phase. And if they are passing in the opposite direction, suppose P is passing like this and P0 is here, okay. So therefore the phi will be here. So therefore I will, for this position, I will say that these P and P0 are in opposite phase, okay. Suppose the time is measured from the instant when the particle moving on the reference circle was at a point different from B, okay. Say at P0, okay. Now POB is phi, then the displacement is basically y. So y equals to that will be ON of n from the equilibrium position O after at a time t will given by, that will be OP sine angle POB, right. So what is POB? That is basically, OP is nothing but the radius, that is A, sine omega t plus phi, okay. So if it is plus, then we can say that they are in the same phase, and it is also called, this part omega t plus phi is called the initial phase or epoch, okay. Now if for the second position, that is here, that is if instead of this, if P0 is here, okay. the position will be same thing, just the equation will be a sine omega t minus phi. Okay, here minus phi is the epoch of n, but when it is minus, we are saying that they are in the opposite phase. Okay, so today I am ending this video. In the next video, I will continue with the velocity of SHM. Thank you.